of the Academy of Science. He will talk about homogenization of convolution type of non-local operators. Please.
Thank you for the introduction, and I would like to thank the organizers for the invitation to participate in this workshop and in the whole program, and for the possibility to give a talk. The talk is based on the joint works with Andrey Piatnitski, mathematician from Trieste, Maurice Kassmann from Bielefeld, and Elena Zhizhina, who is from Moscow and who will speak just after me. And the talk will focus on several homogenization problems for different classes of non-local convolution type operators, both in periodic and random media. So we will consider convolution type. We will begin with convolution type operator with integrable kernel, and should say that there is a huge difference between the behavior of a convolution type operator with integrable kernel and the non-integrable kernels, let's say Levy type operators. Okay, I think in this audience, majority of people know that it's the behavior is totally different. Then we'll discuss homogenization results for elliptic zero-order convolution type operators for in the symmetric case. I will discuss briefly the introduced characters and the difficulties which appear when studying this operator if we compare this with differential operator. Then we will proceed with the non-symmetric case. And finally, in the final part of the talk, we will consider operators with non-integrable kernel and compare the homogenization result for these two classes of operators. So, operators with integrable kernel, we assume that they have this form. You see, A is an operator which has a kernel which is a product. In fact, it's not necessary that it has the structure of the product, but it is much easier to deal with operators with this product structure of the kernel. So A is a convolution kernel, and lambda is a function which represents the local characteristics of the media. It might be periodic, stationary. Well, it basically the same thing as the coefficient in the elliptic operator in the case of PDEs. So what we assume here is that the kernel A of Z is its non-negative function. In some cases, it has the meaning of just probability distribution density. And we assume that it is integrable in integrable function. And lambda is a bounded and uniformly positive. Uniform positiveness is required for uniform coercitiveness or uniform ellipticity, if you prefer. Without this condition, the problem, it's a very interesting problem, it's a challenge, but the problem is getting much more complicated if we don't assume uniform ellipticity. As I told you already, the function lambda represents the local characteristics of the medium, and the function A here is responsible for the typical range of interactions or for the localization property of the operator. Under the above assumption, this operator A is bounded in L2 of Rd, and moreover, its norm admits this estimate. You see the product of L1 norm of A and L infinity norm of lambda. Since we are going to consider also non-symmetric case, it's natural to consider the corresponding evolution equations and formulate the homogenization properties in terms of the behavior of the corresponding semigroup of operators or just behavior of in time of the corresponding Markov processes. The corresponding parabolic equation has this form. Time derivative of u is equal to au. Of course, we will equip with some initial condition to make it have a well-posed Cauchy problem. So, in order to study large time behavior of the corresponding Markov process or the semigroup, it is natural in our framework to make a diffusive scaling of spatial and temporal variables, which has this form. So we multiply a spatial variable by a small parameter and temporal variable by the square of this parameter, assuming implicitly that we expect the results of central limit theorem type. Well, after scaling, our parabolic equation takes this form. You can check that this power 1 over epsilon to power d plus 2 is a correct power because power d comes from the Jacobian when we change the variable in x, and epsilon square comes from the change of variable in time. We divide by epsilon square both parts to have on the left side again just d over dt. Well, and a little bit about applications. Zero-order convolution type operators, they appear in many applications. Some of them are related to different models of population dynamics and continuous contact models. When we study the dynamics of some typically plant population, we immediately arrive at some evolution equation with non-local convolution type operators. Also, in several models of porous media, we also face the necessity to study the operators with integrable kernels. And as usually in homogenization theory, when we study the large time behavior of such system, we naturally arrive at some homogenization problem for these operators. So a little bit about existing results for non-local operators. There was a work by Mariko Arizawa, who studied the Levy type operator in periodic media with oscillating coefficient, but in his case, the kernel lambda, function lambda, depended only on x, not on both variables. Then there was a good, interesting work by Remy Rhodes and Vincent Vargas, who studied the one-dimensional model in one-dimensional stochastic model for Levy type processes. Then there was a interesting work by Nicholas Andrich, who studied another class of Levy type, homogenization of another class of Levy type operator with periodic coefficient. Also, I would like to mention the work of Russell Schwab, who studied non-linear integral differential operators. And recently, there were very nice results by this group of mathematicians, Chen, another Chen, Kumagai, and Wang, who studied the operator with non-uniformly elliptic coefficient with degeneration, and also who studied in periodic media the Levy type operator in the non-symmetric case, which is a very non-trivial problem. Well, it's time to formulate our assumptions on the coefficient. So the first one was already formulated. It's integrable function, which is non-negative, and the assumption that it belongs to L2 is just technical. In fact, it can be dropped at the cost of additional technicalities, so I don't want to do this extra technical work. So we assume that A is both L1 and L2 function. Then, as we discussed this already, we assume the uniform ellipticity. So the coefficient lambda is greater than one positive constant and less than another positive constant. And finally, okay, normalization is not a restriction. We can assume instead of one any positive constant, the result will be the same. But what is important for us that the function a has a finite second moment. That's a crucial assumption. Without this assumption, the result would be totally different. Well, and on top of these assumptions which were formulated, we also assume, we begin with the case of periodic coefficient. So now we assume periodicity and symmetry. The simplest case, of course, is the periodic case and the symmetric case. Symmetry means that A is an even function and lambda is a symmetric function. Well, so in order to formulate what homogenization is, we first consider the operator which a little bit of spectral shift, because clearly the equation just epsilon u is equal to f is not well posed, because 0 is the point of the spectrum of operator a epsilon. It's easy to check. So we choose a positive constant m, and we make a spectral shift and consider the equation mu minus a epsilon u is equal to f. Simple lemma states that this equation is well posed and it has a unique solution. Why? It's very easy to check that the quadratic form corresponding to our bounded operator a epsilon has this form. So this operator is non-negative. It's a simple exercise to check that we have this equality. And since operator is non-negative and symmetric, just by the classical spectral theorem, we immediately obtain that the norm of u epsilon is not greater than 1 over m. So we have a priori estimates which is uniform in epsilon. Now we give a definition of homogenization. Maybe in this audience everybody knows, but still, for the sake of completeness, let me formulate this definition. Let me give this definition. We say that the family A epsilon admits homogenization as epsilon goes to 0. If there exists an operator A0 such that this problem mu minus a0u is equal to f is well posed, so for any f it has a unique solution, and u epsilon converge to u0 in L2 space as epsilon goes to 0. We call a0 the effective operator. Well, and now since again, to be prepared for studying non-symmetric operator, we all give another definition of homogenization related to the parabolic case, to the semigroup convergence. So we consider also the parabolic Cauchy problem for the parabolic version of our operator, which is here, dtu is equal to epsilon u. And with initial condition u0, and we say that the family admits homogenization if solution u epsilon converge to the solution of this limit Cauchy problem. Well, the first theorem in symmetric periodic case, under all the above condition, which C1, C3, you remember, and then periodicity and symmetry. The family epsilon admits homogenization, and the limit operator is divergence form, second order elliptic partial differential operator. So for any function from L2, f from L2, the solution of equation m minus a epsilon u is equal to f converge as epsilon goes to 0 to the solution of equation m minus a hom U is equal to F. It's important to emphasize that the matrix A home is positive definite, so it's a true elliptic operator. So in this audience, maybe this is natural, but for the specialist in partial differential equation, it's a kind of surprise that we start with the family of bounded operator, and in the limit we have the operator with locally bounded resolvent. So the limit operator has not the same structure as not the same type as the original one. So maybe I don't have time, so maybe I skip here the ideas of the proof. We use usual expansion, and just one comment, we use usual asymptotic expansion. We assume that our corrector chi is periodic function, and the difficulty which appears here is that we would like to have different arguments for chi, but the same argument for function u0 and gradient u0, because it should be just a common constant for everybody. But here we have different arguments. And the trick is to having in mind that we have very strong localization property, and only small, only the value of y which is close to x will play a role. We expand function u0 and its gradient in Taylor series, and this allows us to replace the argument y with the argument x at the cost that there are extra terms coming from higher order Taylor coefficients. That is written here, and then after substitution we obtain the cell problem, periodic cell problem for the corrector, and show that in the symmetric case this problem is well posed and it has a unique solution up to an additive constant. So I skip the proof because I don't have time, and we proceed directly to non-symmetric operators. We still assume periodicity, but we do not assume the symmetry anymore. And we consider the Cauchy problem, which is written here. And our first important result is the result on a priori estimates for U epsilon. It turned out that there is a constant which doesn't depend on epsilon, such that this Cauchy problem admits, solution of this Cauchy problem admits this uniform estimate. So this L infinity 0t L2 norm of U epsilon is uniformly bounded by C times L2 norm of the initial condition. Well, similar result holds for the equation with the right-hand side. So similar theorem also holds for the equation with the right-hand side. The only difference that now the constant C, it doesn't depend on epsilon, but it does depend on the time interval on which we study our problem. But this is natural. In the presence of right-hand side, of course, if we have a source, then the time appears, time interval appears in the constant, in the estimate. Well, here there is an interesting periodic cell problem. We consider the cell problem on the torus. We are in a periodic framework, so auxiliary problem are defined on the torus. We introduce the joint operator. The original operator has a simple eigenvalue at 0. This eigenfunction is equal to 1. It's easy to check that 1 is an eigenfunction, and it's a simple eigenvalue 0 due to the maximum principle. There are no other eigenvalues. So the joint operator also has a unique eigenfunction, but since this operator has a rather complicated structure, it's the sum of compact operator and operator of multiplication by function, the adjoint operator, Crane-Rootman theorem doesn't apply directly, so it requires some work to obtain the following result. The kernel of adjoint operator on the torus has a dimension 1, which is natural, but what is important for us is that the corresponding eigenfunction, of course under proper normalization, admits lower and upper bounds by two positive constants. And the operator is Fredholm. If there is a right-hand side, the equation is solvable if and only if the right-hand side is orthogonal to the kernel of this adjoint operator. Well, perfect. Now we can formulate the result in the non-symmetric, for non-symmetric operators. You see, there is a constant vector B, which in general is not equal to 0, and a positive definite matrix A home, such that the difference between original solution and limit function evaluated in moving coordinates. You see, in set of x, we substitute x minus b over epsilon t, so it's linearly moving frame. And in this linearly moving frame, we have convergence in L2, which is formulated like this. And the limit operator is again the standard heat equation. So this theorem comprises, if we can think about the corresponding Markov process, it comprises both the law of large number and b is the velocity, and the central limit theorem. A home is the corresponding covariance matrix. Well, in the stochastic case, we can deal only with symmetric operator. We don't know how to deal with non-symmetric operator. It's an important challenge in this theory. So now we assume symmetry, and we assume that our function lambda is statistically homogeneous, both in xi and eta. For example, we can consider these finite sums of products. I don't go into the details, they are rather standard. And then theorem states that, like in periodic case, we have almost sure quenched result, homogenization result. And the limit operator is again the just elliptic second order operator with constant coefficient, with matrix which is also deterministic. Well, there are two ways to prove this result. One is the corrector technique, and the corrector technique is rather technical here because corrector is quite complicated. And another technique is using subadditive ergodic theorems, which also faces some difficulties related to non-local nature of the operators. Well, and in the final part, I would like just within 1-2 minutes to describe the results for the Levy-type operators. So we have, again, the Levy-type operators with variable coefficient. Lambda might be periodic or random. And in periodic case, with some additional restriction, we can also consider non-symmetric case. So we start with the symmetric case, and in the symmetric case, we have the following periodic symmetric case, we have the following homogenization result, that as epsilon goes to 0, the solution of this equation mu minus a epsilon u for any right-hand side f converge to the solution of the limit equation, and the homogenized operator has this form where lambda 0 is just mean value of the function lambda. So here there is no corrector, it's just mean value. Similar result holds holds in this symmetric random case. Of course, in this case, instead of mean value, we should just take the expectation. And the last result is for the case of non-symmetric periodic case. And here we assume that the coefficients lambda are Lipschitz continuous function. And in this case, we can prove that the kernel of this operator, of the adjoint operator, also exists and admits this bound, which are formulated in this theorem. It's bounded from below and above by two positive constants. And then I forgot to write here that alpha in this case should be less than 1, not from 0 to 2, but from 0 to 1. And lambda should be Lipschitz continuous. And in this case, we can prove homogenization result in non-symmetric case. And in this case, the effective coefficient is given by this formula. You see, the kernel of the adjoint operator is involved in the construction of the limit function. Well, and the open problems are on which we work now, operators with asymptotically high contrast coefficient in high contrast media, stochastic homogenization in non-symmetric case, at least in the case of finite range of dependence, then a kernel with random and time coefficients, and also estimate for the rate of convergence. Well, here are some works which were basis for this talk, and thank you for your attention.
Thank you very much, Professor Piatnitski, for your very beautiful and clear presentation. I am first asking the audience whether there are questions here.
Could you please explain the numerical procedure that computes the effective matrix A homogeneous?
Numerical procedure, what do you mean?
Somebody want to compute this matrix, effective matrix, A homogeneous. What is procedure to do this?
Well, in periodic case, both in fact in periodic and in random case, we first construct a corrector. In periodic case, it's not a difficult problem. It's problem on the torus with quite nice operator. So we construct a corrector. We know that there is it exists and is uniquely defined. And then in terms of the corrector and the coefficient of the operator, there is explicit formula for the effective coefficient. In random case, picture is similar, but the construction of corrector is rather implicit. We just prove its existence. So then for numerical simulation, we can think like in the case of partial differential equation. We can think about some periodic approximation with growing period or something like this. But I think there are no how to say, no nice way to construct explicitly the corrector in the random case. But it exists, and the effective matrix is given, is an explicit expression in terms of the coefficient and the corrector.
Thank you very much. Here was another question.
Yes, thank you for the talk. I'd like to ask, it's very often in fractional, for example, calculus, we're interested in your kind of inversion, but when m equals to 0, can you say something about convergence if m is not positive but equals to 0?
Then I don't know. We're at the edge of continuous spectrum, and presumably we should assume something more about the right-hand side. I don't know. We didn't think about this problem.
Okay.
Sorry.
So let's thank our speaker, our first speaker today. Oh, now there is one. sorry, we just checked and Enrico.
Oh, yes, sorry. Very quick question. So if you can give me an intuition on what is the effect of this homogenization procedure on the underlying stochastic process. So if you see these operators as semi-group generators, what is happening to the stochastic processes?
For the stochastic process, at least if the coefficients are not too ugly, but let's assume that they are continuous, then we have the homogenization result plus some work to prove some compactness result. Combining this homogenization result and compactness argument, we can obtain invariance principle in the Skorokhod-Topol space for the corresponding Markov processes.
Okay, so you need tightness, compactness, tightness, additional. Yes. Thank you.
Yes,
very much.
of course.
Yes,
Otherwise,
yes.
just homogenization doesn't give.
Of course, yes. Thank you very much.
Only single point distribution. Yeah.
Yes. Thank you very much.